Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about dimensionality reduction using principal component analysis. Here, dimensionality refers to the number of features associated to each data point in a dataset. Datasets with high dimensionality, where many features are associated to each data point, can be computationally expensive to process and difficult to analyze and visualize. Dimensionality reduction techniques alleviate this by embedding the data in a lower dimensional space. As we will show in this video, principal component analysis is very useful for this purpose. Let's get to it. We're going to talk about dimensionality reduction via principal component analysis, and our main motivation is that data with a large number of features can be difficult to analyze and process. A possible solution is to apply dimensionality reduction techniques that reduce the dimensionality of the data while preserving as much information as possible. This is a very important pre-processing step in many applications. Today we're going to discuss linear dimensionality reduction, where we perform the dimensionality reduction by taking the inner product of each data point with a predetermined basis of vectors. Let's see what I mean by this. We are going to model our data as samples from a d-dimensional random vector x. For simplicity, we will assume that x has zero mean, but otherwise we can always center it by subtracting its mean. Now let's consider the representation of x in an arbitrary orthonormal basis where b1 to bd are d-dimensional vectors that are unit norm and orthogonal to each other. By basic linear algebra, we can represent x exactly, because it's a d-dimensional random vector, in terms of the coefficients, its coefficients in this basis of orthonormal vectors. How do we get each coefficient? We take the inner product of the corresponding basis vector with x. And because the basis vectors are all orthogonal and unit norm, then this representation is exactly equal to x. Okay, that's just basic linear algebra. Now we have an equivalent representation of x in terms of these coefficients. However, the representation is d-dimensional, so we haven't gained anything. An idea suggested by this, however, is that maybe we could just use a subset of these coefficients. So our idea is going to be to use the first k here. The fact that they're the first k is obviously arbitrary, but we're going to use a subset of k coefficients to represent the random vector, and that's going to provide us with a representation of lower dimensionality. It will be the dimensionality of the representation will be just k. If we consider how well we're approximating the random vector, then it's reasonable to take a look at the truncated representation, where now we're not summing d vectors, we're summing only k vectors. This approximation will tell us what information we're losing about the random vector. Notice that at the end of the day, the representation is going to be in terms of these coefficients. But if we want to check how well we're approximating the original vector, we still need the basis vectors here if we want to build this approximation. But the actual representation I want to emphasize is based on the coefficients. This will become much clearer when we look at some examples in a few moments. Before that, let's consider a key question. How are we going to choose the subset of k orthonormal basis vectors that we're going to use to reduce the dimensionality of our random vector that represents our data? A reasonable way to go about this is to consider this the composition of the original random vector, which, as we have said, can be represented in terms of the basis vectors. We can decompose that original random vector when represented in the basis vectors into the component that we're preserving, because we're going to use these coefficients as our representation, and the error, the component that we're not preserving. We would like this guy to capture as much information as possible from the original random vector, because then that means that these coefficients here are going to preserve that information in a certain way. That's the intuition here. So now we can consider the L2 norm of the random vector. And here I want to emphasize that this is a choice that we make. We're going to care about, if you want, the length of the vector in Euclidean space, which is the L2 norm. There could be other metrics that might be more meaningful for specific applications, but this is a very reasonable general purpose metric. Now, if you realize, because these guys are all orthogonal, this whole vector is orthogonal with this whole vector. Okay, the approximation is orthogonal with the error. So, by Pythagoras' theorem, if we look at the squared length of this vector, the squared L2 norm, is going to be equal to the sum of the L2 norms, the squared L2 norms of the two components. This is very useful because now we can express this error that we want to minimize. Remember, we want to make sure that this guy captures as much information as possible about the original vector, because we believe that then this will give us a dimensionality, a representation of reduced dimensionality that will be higher quality in some sense. So we want to reduce that error. Now we can express the error in terms of the L2 norm of x minus this term here, which intuitively captures how much of the original vector is preserved in the representation. We want to make this error as small as possible, so we will want to make that as large as possible. Now these guys are orthonormal vectors, so this L2 norm squared can be written in terms of these coefficients. Because those guys are orthonormal vectors, this is just equal to the sum of the squared coefficients. This follows from basic linear algebra. If you don't remember these details, maybe you can review the properties of orthonormal vectors. Or you can just trust me, this L2 norm is equal to this sum of squared coefficients because of the fact that B1 to Bk are orthonormal. All right, so we have arrived at an expression for the squared L2 norm of the error, which is the squared L2 norm of the original random vector minus the sum of squared coefficients. Remember that we can express these coefficients as the inner product between each of the basis vectors and x. This term does not depend on the chosen basis vectors, but this term obviously does. So a reasonable choice is to try to pick those subset of k vectors that maximize this term, because that will minimize the error. I almost got confused there between maximize and minimize, but we want to maximize this term because that's how much information is preserved in our representation of reduced dimensionality in order to minimize the error. This is a random quantity, okay? Remember that when we see a squiggly line up here, that means that the quantity is random. So what do we mean by minimizing the error if it's a random quantity? We're going to minimize the mean of the error. That makes sense, by the way, because this is a non-negative quantity. So it makes sense to minimize its mean. Otherwise, it could be problematic because there could be cancellations. Okay, so we want to minimize the mean L2 norm error, and we've seen that this is just equal to the mean. We're applying here the linearity of expectation. This is the mean of the original, the L2 norm of the original random vector, which does not depend on the representation. And here we have the sum of the mean of these coefficients, which are given by the inner product between Bi transpose x squared. Now, this guy is a random variable. It's a random variable that has zero mean because the mean of x is zero. So by linearity of expectation, the mean of Bi transpose x is also going to be zero. If we have a zero random variable and we're looking at its mean squared, that's just equal to its variance. So here we have that the mean L2 norm of the error is equal to the mean L2 norm of the original signal that we cannot, the original random vector that we cannot modify, minus the sum of the variance captured by each of these directions, each of the orthonormal vectors. Because remember, from our discussion on principal component analysis and the covariance matrix, that this inner product essentially gives us a projection of the random vector in a specific direction, in the direction of Bi, because Bi is a normalized vector with unit norm. And the variance of that projection basically tells us how much the random vector varies in that direction. So we have this sum of variances in these k orthogonal directions. What should we choose for B1 to BK? What choice of B1 to BK maximizes the directional variance? I will let you think about that for a couple of seconds, or you can stop the video. But we've talked a lot about this, right? We talked a lot about this when we introduced principal component analysis. The principal directions of the random vector, which are obtained by computing the eigenvectors of the covariance matrix, satisfy the following property by the spectral theorem. The first eigenvector that is associated to the largest eigenvalue maximizes the directional variance. If we're orthogonal to that vector, the directional variance is maximized by the eigenvector corresponding to the second largest eigenvalue, and so on and so forth. So because of this, it seems very reasonable to pick as the basis vectors for our dimensionality reduction approach to pick the eigenvectors of the covariance matrix corresponding to the k largest eigenvalues of the covariance matrix. We call these vectors U1 to UK because we order the eigenvalues from largest to smallest. It turns out that this is optimal. This choice of eigenvectors minimize the mean L2 norm error that we were considering before. The corresponding representation is in terms of the inner product of the eigenvectors and the random vector x, which is exactly equal to the principal components of the random vector. So we're going to end up using the first k principal components of the random vector as our k-dimensional representation of the random vector. And again, this is optimal. It's not immediately obvious why optimality follows from the spectral theorem. We're going to prove this at the end of the video. But before we do that, let's make sure that we understand how exactly we use principal component analysis to perform dimensionality reduction. So imagine that you have a data set. Well, we're going to look at an example that involves this data set, which is a very typical data set that you see in data science, which are some wheat seeds that belong to three varieties, Kama, Rosa, and Canadian. I have no idea about wheat varieties, but in our data set, we have those three wheat varieties, even though my grandparents actually used to cultivate wheat. And I remember playing on piles of wheat when I was small, but let me not ramble. Okay, so each wheat seed, like each data point corresponding to a wheat seed, has the following features: the area of the seed, the perimeter, the compactness, the length of the kernel, the width of the kernel, the asymmetry coefficient, and the length of the kernel groove, whatever that means. This is great, but it makes it very difficult to visualize because now, you could visualize pairs of features and that would be meaningful, but you would have to choose among all the possible pairs. Instead, we can try to find the two-dimensional representation that captures the most structure in the data. Again, we make the choice that we want to capture the most L2 norm, so to preserve the mean L2 norm of the data as much as possible. If that is the case, then we will use the principal components to represent the data. Intuitively, we're trying to capture as much variances in the data as possible, as we showed. Of course, I should have, shown you this question and then, talked about what we want to do. But anyways, how do we visualize the data in two dimensions? I gave it away. We show the two principal components. How do we exactly do this? Well, we compute the sample covariance matrix of the data. That is going to be 7 by 7 because we have 7 features. D is equal to 7 here. We compute the eigenvectors of the covariance matrix. We pick the two eigenvectors corresponding to the largest eigenvalues, and then we compute the inner product of each centered data point where we have removed the mean, computed over the whole data set, and the corresponding eigenvector. What do we obtain? We obtain this graph here where we're plotting using the first principal component of each data point against the second principal component of each data point. And what we see is that we actually preserve the structure in the data very effectively because the varieties of wheat are actually separate. I want to emphasize that the dimensionality reduction approach that we followed did not take into account the fact that there are 3 varieties. This is just a sanity check to see whether some meaningful structure in the data was preserved. If you want to do something that really separates the 3 varieties of wheat, then you would use some kind of supervised classification approach to train a classification model. But this just shows that our approach, where we're trying to preserve as much variance as possible, does preserve important structure in the data. Now I want you to think about what would happen if we did this, but with the 2 last principal components. What do you think we would see? Again, pause the video if you want. Well, what we see is a useless representation where everything is bunched right at the center because we're capturing essentially no variance in the data. This is just a sanity check about why we're choosing the first principal components as opposed to the last ones. These guys preserve the most variance. These guys preserve the least variance. Now let's take a look at another example with an even higher dimensional data set. Here we're going to use this image data set that we had previously looked at in the video on principal component analysis, where each image contains 4096 pixels, and we're going to represent each image as a very long vector, okay, where the vector has dimensionality 4096. In order to center the data, we will remove the sample mean. We already took a look at the principal directions corresponding to this data, but this is just to show you. Here what we've done is we've computed the sample covariance matrix of the data, and then we've computed the principal directions. So these are the first principal directions. This is the vector that captures the most variance, the second vector that captures the most variance, which is orthogonal to this guy, and so on and so forth. What we see is that the first principal directions capture coarse level details of the head, of the face, such as the eyes, also illumination. Illumination seems to capture seems to be very important this seems to account for a lot of variance in terms of pixel intensity. Here we also see illumination and other features such as the mouth or the nose. The reason why I point this out is that as we go to, by the way, this is the variance captured by each of the eigenvectors. So here you can see that this guy captures a lot of variance compared to the rest. The finer details seem to be relegated to later and later. I don't know if later is the word, but to eigenvectors corresponding to eigenvalues, to smaller eigenvalues, because these finer scale details don't capture as much variance. In some cases, however, some of these fine scale details might be important for downstream tasks. I bring this up because what we optimize when we perform dimensionality reduction with principal component analysis is that we preserve as much variance as possible, but that doesn't mean that we're preserving necessarily all the feature properties that are important for a specific downstream task. It's just a general purpose way of reducing dimensionality. It might not be optimal for certain specific applications. And here we see some of the eigenvectors that capture very little variance. They look very noisy-like, although they clearly have some fine-scale structure in them. All right, so now let's consider a low-dimensional representation of a face, in particular a 5-dimensional representation of a face. The representation will correspond to the 5 first principal components, which are these guys. But we can also consider what is the approximation in the original 4096 dimensional space so that we can see what information we're losing. In that case, we can reconstruct the face corresponding to just these 5 principal components by multiplying the principal components by the corresponding principal directions and adding back the mean. This will become clearer when I show you the picture. So this is the approximation corresponding to, I'm going to use the same color, these 5 principal components, obtained by taking the corresponding data point, centering it, removing this guy, and then taking inner products with each of the principal directions. To see what information we are losing, we can reconstruct the low dimensional phase, if you want, in the original space by multiplying each of the components with the corresponding principal directions, adding back the mean, and what we see is that we have preserved mostly coarse level structure in the phase. That's what we have preserved in this 5-dimensional representation of this phase. Let's take a look at the original phase. That's the original phase. So as you can see, we're losing a lot of information, but we're going from a representation that has 4096 dimensions to just 5 dimensions. So obviously we're going to lose a lot of information. Okay, this is how it looks, the 5-dimensional representation. What if we had taken more dimensions than the original, when we project back onto the original space? Because remember that here, the representation only depends on 5 numbers. Here it only depends on 10 numbers, and so on and so forth. But we can look at the corresponding approximation in the original space to see what information we're losing. And what we see is that at the beginning, we definitely lose the direction of the phase. We lose the glasses here, but here we already see them a little bit. The mustache, we don't see it. The mustache emerges when we already have 20 dimensions. Then for k equals 30, actually the approximation is pretty good, but we don't have the direction of the phase. The direction of the phase is starting to be recovered. No, actually here for 50 it's not recovered, but for 100 it is. And then for 300 the approximation is actually really good. Okay, so again, each of these representations has 5, 10, 20 numbers, but we're comparing them to the original by projecting them back to the original space and looking at how good the approximation is, okay? So what we're actually optimizing, and the metric for which principal component analysis is optimal for dimensionality reduction, is taking this guy and taking the mean L2 norm error with this guy when we fix k equals 5. And the optimal dimensionality reduction for that metric is picking the 5 first eigenvectors of the covariance matrix that correspond to the 5 largest eigenvalues. Again, that might not be optimal for certain downstream tasks such as classification. Great. So that brings me to an application of dimensionality reduction as a pre-processing step. This is a bit of a toy example because nowadays, if we wanted to do face recognition, we just use a convolutional neural network or some other deep learning approach. But the good thing about it is that we're going to be able to kind of sanity check what the dimensionality reduction technique is doing. So I kind of like this example. Our goal is to identify a new picture, identify whether it corresponds to each, identify to what person it corresponds in our training dataset. So we have a training dataset of faces where we know the identity associated to each face, and now a new picture comes in and we want to identify the person. We're going to do this in a very naive way where we just apply nearest neighbor. We take the picture, we compare it to all of the pictures in the database. The closest one is going to be our estimated identity. This only works because in our data set, the faces are very registered. Otherwise, if people are looking in every direction or the face appears in a corner or something, this would really not work because the pixels would not align. That's why you need something like a deep neural network to do this effectively in practice. But here we have registered faces, so that's okay. We apply our nearest neighbor classification and it actually works quite well. The problem is that it's very expensive because we have to compare all the pixels of each face and we have to compare all of the faces. So the complexity is n, where n is the number of data points in our training data, and d is the number of pixels in each face. We want to reduce this complexity, and we're going to do that by applying principal component analysis, and this illustrates an important application of dimensionality reduction techniques where we use them as a pre-processing step. First, we reduce dimensionality, and then we apply some other kind of analysis or processing on the data. Okay, so we're going to apply classification in reduced space. What we're going to do is we're going to compute the sample mean and the k-first principal directions using the composition of the sample covariance matrix from the training data. Then for each test data point, we're going to center the test data point using the training sample mean. We're going to compute the k principal components using the principal directions from the training data, and that is going to give us k principal components that we're going to compare to the k principal components of each of the data points in the training set. So we're going to perform this comparison in L2 norm over the whole training set, but now these guys are only k-dimensional. So we have reduced the complexity of performing these comparisons to nk. What I'm kind of sweeping under the rug is that we're computing the first k principal directions, which can be expensive. Although if k is small, it can be also not so expensive. You use certain tricks such as the power method or randomized PCA and so on. That gets a little bit technical, but it's important, right? Like performing eigendecompositions of extremely large covariance matrices might be computationally costly. For the purpose of this example, we're kind of sweeping that a little bit under the rug. The thing is that once you have that, then for every test point that comes in, it's true that the cost has been reduced to nk. Great, so now let's take a look at the results. When we use a k, so this is k, when we use a k that is very small, we get a lot of error because we're not preserving enough information from the original data points. But soon, for actually very small k, like 16, 17, the error really goes down. We're just making 5 mistakes. The test set contains 40 phases. And then eventually, actually for dimensionality 42, we already get the same error as if we're using the full dimensionality. Okay, so we have dramatically reduced the dimensionality and still we preserve the same performance. This shows that we're capturing the important information in the data to perform this identification. Let's take a look at some examples. So this is one of the original test phases. This is the approximation to the test phase that we obtain in the way that I just mentioned. Okay, so the representation would be actually just 42 numbers, but we can go back to the original space by adding up the sample mean and weighting each of those numbers by the corresponding principal direction, and we see this phase where we're obviously losing a lot of the fine scale details, but it's actually a pretty good approximation. This is the closest phase in the training set, and it corresponds to the same person, so we get it right. This is the actual phase in the training set. This is the approximation obtained by projecting on this 42-dimensional space that corresponds to the 42 first principal components. Let me show you a couple of other examples. For this guy here, this is the approximation. Again, this is a test image. This is the closest approximation in the training set. And this is the original training image. Again, we get it right. Now this woman here, notice that in the 42-dimensional space, we have lost a little bit of the tilt in her face, but that's probably not very important for identification. This is the closest phase, and we get it right again. This brings up an interesting question, which is the information that we're not preserving in the dimensionality reduction can actually hurt you for classification if it's important, but it can also help you, because imagine that we just, through the dimensionality reduction, we kind of correct the way people are looking directly. That actually could help us for classification, because the way people are looking is not important to discriminate their identity. It can also hurt us if we're missing some details because of dimensionality reduction that are important for the classification. So it's unclear sometimes whether dimensionality reduction is actually going to help you or hurt you for certain downstream tasks. Let's take a look at this last example. Here, we lose a lot for this particular person. We lose a lot of details with our dimensionality reduction. In fact, it almost appears that some glasses appear. And this actually results in a wrong identification, because this is the closest phase among the training set when we just use the 42 dimensions, and we get this wrong. So this is an example where our approach does not work. Okay, so I've shown you how to apply principal component analysis for dimensionality reduction, and the motivation was that it's optimal in the sense that it preserves the variance in the data, or equivalently, it minimizes the mean L2 norm error of the approximation in the original d-dimensional space. But we have not actually proved it. We have not proved that this representation, where these guys are the k first principal components, is actually optimal. So we'll do that before finishing the video. In order to do that, we need to show that the mean error is minimized by the first k principal directions. How are we going to prove this? We're going to apply induction. Oh, actually, I kind of jumped the gun there. Before applying induction, we're going to represent this mean error in terms of the mean square of the original random vector minus this sum of variances, which we showed at the beginning of the video are exactly equivalent. Okay, remember, we want to maximize these guys. We want to show that the first k principal directions capture as much variance as possible. In fact, the sum of the variances is going to be optimized. Okay, we're going to show this by induction, as I said a couple of seconds ago, on k. First, we show that this is true. It's true that this is minimized by the first principal direction for k equals 1. And then we show, okay, let's actually do that because that's very easy. We know by the spectral theorem that the first principal direction associated to the largest eigenvalue captures the most variance. So we're done. This is the basis of induction, as easy as that, directly by the spectral theorem. Now, once we have the basis of induction, what we're going to show is that if this is true for k minus 1, then it is true for k. And that's going to complete the proof because it's true for 1, so then it's true for 2, 3, 4, and so on. Okay? But we still have to do this. We're going to assume that it's true for k minus 1, and now we have to show that this directly implies that it's true for k. How are we going to do that? Well, we're going to fix an arbitrary set of k orthonormal vectors b1 to bk, and we're going to show that this sum of variances is smaller or equal to the variances, the sum of variances captured by the first k principal directions. If we assume that the induction hypothesis holds. Okay? In order to do that, it's going to be useful to represent this sum of variances in the following way. Remember that they're just equal to the sum of mean squares because this guy is zero mean, as we said at the beginning. And by linearity of expectation, we can actually put the sum inside. So now we have this sum of coefficients, which is actually equal to the squared L2 norm, because these guys are orthonormal vectors, the squared L2 norm of this vector here, okay, which is built by taking those coefficients and multiplying by the corresponding basis vector of these k arbitrary basis vectors that we have fixed. Now we can geometrically interpret this as the projection of the original random vector onto the span of b1 to bk. What is the span of b1 and bk? It's the subspace of all linear combinations of b1 and bk, of the basis vectors b1 to bk. These k basis vectors are orthonormal, so the projection is exactly equal to this. We take an inner product with each of the basis vectors, we multiply by the corresponding basis vectors, and then we sum. Again, this is just by basic linear algebra. You might want to review projections and orthonormal basis vectors. But the point is that we have this projection here, and that's exactly equal to this variance. We want to show that if we that basically the sum of the variances of the first k principal directions are going to be larger. I'm getting a bit confused there. The sum of the variances of using the first k principal directions is going to be larger than this term here. Okay? In order to do that, we're going to use a key insight. The key insight is that we can actually use any basis of this subspace S, which is formed with the linear combinations of B1 to Bk, to compute this projection. So here we used this specific basis of this subspace, but we could have used any other basis as long as they belong to the subspace. This is just by properties of the orthonormal vector. You can think of the subspace as some hyperplane. If we rotate the orthonormal basis while staying in the hyperplane, the actual point does not change. Okay, hopefully that geometric intuition helps. And now we can choose this basis wisely to prove the result that we want to prove. How do we choose this wisely? Well, if this subspace S has dimension k, we're going to be able to find at least one vector A, that I'm going to call like this, a perp, that is orthogonal to the first k minus 1 principal directions. What is my agenda here? Well, you will see in a moment. This is going to decouple the inequality in the variance between an inequality that only concerns the kth principal direction and an inequality that only concerns the first k minus 1 principal directions. And for that, we're just going to apply the hypothesis of induction. Okay, so first, if this guy, oh, and by the way, this is true because S has dimensionality k, because it's spanned by k orthonormal basis vectors. If this were not true, if we cannot find a vector that is orthogonal to u1 to uk minus 1, that basically means that the whole subspace is in the span of u1 to uk minus 1 and its dimension k minus 1. So for sure we can find one vector that is orthogonal to this k minus 1 principal directions within the subspace. Now this is important because can that vector that is orthogonal to all of these guys capture more variance than the kth principal direction? If you remember our video on principal component analysis, no, it cannot, because by the spectral theorem, the kth principal direction is the one that captures the most variance once you are orthogonal to the first k minus 1 principal directions. So things are already looking good because this guy captures at least as much variance as that guy. So as I said, this wise choice kind of decouples the kth principal direction and the rest, because what we're going to do to build the basis for S is to pick AK to be equal to this A perp that is orthogonal to the first k minus 1 principal directions, and then the rest are going to be picked so that they span S. S has dimension k, so there's going to be k minus 1 other vectors together with A perp that form the subspace. Now we've done essentially all the work we needed to do, because we've shown that already by the spectral theorem the kth principal direction captures at least as much variance as this A perp. And now for the rest, we can apply the hypothesis of induction. The sum of the variances captured by these guys is smaller or equal to the sum of the variances captured by the first k minus 1 principal directions by the hypothesis induction. Hypothesis induction, amazing. The hypothesis of induction, I wanted to say, the induction hypothesis. Okay? Now if we sum this basically is almost what we wanted to prove. The sum of the variances captured by the first k principal directions is greater or equal to the sum of the variance captured by A1 to AK. But this is just equal, as we showed before, to the mean L2 norm of this projection onto that subspace, which in turn is equal to the sum of the variances captured by B1 to BK, which is this arbitrary set of k vectors that we fixed at the beginning. So this actually holds for every possible choice of B1 to BK. We showed that this, the sum of the variances was greater. The sum of the variances captured by the principal directions was greater for k equals 1. Now we've shown that if it's true for k minus 1, it will hold for k. So we have completed the proof. The principal directions are the ones that capture the most variance in the sense that they maximize this sum of variances, and hence they minimize the mean of the squared approximation error. And that's it. We have proved that principal component analysis is optimal for dimensionality reduction in that sense. Let's take a step back. What have we learned? We have learned the definition of dimensionality reduction and why it's important. We have learned how to perform linear dimensionality reduction using principal component analysis. And finally, we have proved that principal component analysis is optimal for dimensionality reduction in terms of mean L2 norm error. I cannot say this enough times. That doesn't mean necessarily that it's optimal for certain downstream tasks. But it's a very reasonable approach. It's a very reasonable general purpose approach. And that's all I got. Thank you very much.